was not true. If graph expanders would not exist, that means somehow you would have an upper bound on the expansion coefficient in terms of the size of the graph and the vertex degree, and that would go to 0 as n goes to infinity for each degree. That would be a big theorem, but that's not the way. The expander graphs do exist, and that's what we will construct today. But there was also a couple of interesting things I did last time. So one is this great inequality of Cheeger and Busa, Cheeger inequality. So it tells that the expansion coefficient, which if you remember is the minimum of the edges. This is the edge expansion. Okay, the minimum number of edges coming out of S divided by the number of vertices in S. You take the minimum over all S. So it's the boundary to what is the minimum boundary to volume ratio. That's what it is. So boundary can be measured in different ways. Instead of the edges going out of S, you can also measure vertices connected to S, which are outside of S. That will be called the vertex boundary. But if you stick to d-regular graphs, all these are the same. Anyway, the point of this Cheeger-Bose inequality was that we have this Hg is estimated from below and above by the second eigenvalue of the Laplacian. Okay, lambda 2, or equivalently it's sometimes called a spectral gap. It is the gap between the largest eigenvalue of A and the second largest eigenvalue of the A. A is the adjacency matrix. So this lambda 2, second eigenvalue of L, it's the gap between the first and second. Here is also the gap between the first and second in A, which is d minus. So we stick to d regular graphs, then it is d minus lambda 1, d minus lambda 2, etc. Okay. So construction of expanders is equivalent to constructing a sequence of graphs where the second eigenvalue is bounded below. We want Hg to be bounded below, so lambda gn should be bounded below. That's what was the point of this. Now, as I said, there is a limit to how big the lambda can be. So this is a theorem of Allen and Bopanna that lambda g cannot be larger than d minus 2 d minus 1. Well, it can be, strictly speaking, for finite d and n, but plus some quantity which goes to 0 as n goes to infinity. So in other words, the second eigenvalue of the adjacency matrix is always asymptotically at least 2 d minus 1. So the largest gap is achieved by achieving this 2d minus 1, and those graphs are called Ramanujan graphs. So this, if you can find a sequence of graphs where lambda gn, that is, for me, lambda is referring to the Laplacian. Okay, so if this you achieve this much gap, d minus 2, d minus 1, then that is called Ramanujan graphs, and that is a much harder problem which we won't discuss. Okay. But I wanted to maybe just give an indication of why a theorem like this Allen-Bopanna theorem is true. I won't actually give a full proof, but maybe I want to indicate just a little bit about this. I will spend a few minutes and then we will go to the construction of expanders. But any questions or comments about everything up to last? Okay. Okay, so if there are no questions, comments, then let me just indicate why something like why you can't have a very small lambda. Okay, so just an indication. I won't do a full proof. What we are trying to show is that if Ag is the adjacency, so lambda g, so this is lambda g is less than equal to d minus 2 d minus 1 plus, let's call it little od of 1, meaning this is some quantity that goes to 0 as n goes to infinity for fixed d. Okay. So there is an explicit, you can write an explicit form for that in terms of diameter and so on, but this is good enough for us. Okay, so where G is a d-regular graph. Equivalently, in terms of AG, if AG is the adjacency matrix, matrix. Its eigenvalues are d greater than equal to, let's call it lambda 2 tilde, okay, greater than equal to lambda 3 tilde, and so on. These are the eigenvalues. And it goes up to lambda n tilde. Okay, so lambda 1 tilde is actually d, because each row sum is equal to d. In a d-regular graph, all the row sums are equal to d. So ag times the constant vector 1 is d times the constant vector 1. So this is an eigenvalue 1. And you can also see from the same that this lambda n tilde is greater than equal to minus d. See, if this is a basic fact in linear algebra, that eigenvalues are bounded by, in absolute value, by the sum of absolute values of the rows. I mean, if you have, let's say, if you have a positive matrix, then you take the row sums, and then all the you take, I mean, positive symmetric matrix, take row sums and take the maximum row sum. That is a bound for the absolute value of all eigenvalues. It's a simple fact in linear algebra. So lambda n tilde will be at least minus d. Okay. So what this is saying is that, so this is same as saying lambda 2 tilde. This is the way it's usually written, is greater than equal to 2d minus 1 minus something that goes to 0 as n goes to infinity for fixed. So the second eigenvalue can't be too small. Now I give an indication of proof, not the full proof. In fact, it won't be a proof of this, but it will tell something which is also an important point. So look at how do you get something like this. So one of the very fundamental facts in basic matrix theory is that the trace of a matrix can be written in two ways. Okay, see, the matrix and eigenvalues, there is a subtle relation. It's very hard sometimes. But one thing that connects the eigenvalues and the entries of a matrix is the trace. So if you look at the trace of a matrix, it has two ways it can be written in two ways. Here, let me look at trace of the square of the matrix. On the one hand, it is the sum of squares of the eigenvalues. Okay. On the one hand, it is the sum of squares of the eigenvalues, lambda 1 tilde square plus lambda 2 tilde square plus up to lambda n tilde square. On the other hand, it is also the sum of the, it is the sum of the diagonal entries of A, which is in fact, basically in this case, it becomes Aij squared over all Inj. Sum of squares of all the entries, because it's a symmetric matrix, it is just this. Now, what we know is that this first one is D, right? So this is less than equal to D plus, can I write D plus? All the others are bounded by lambda 2 tilde. Is this okay? So the first one is D squared. The rest of them, can I bound this? So this summation Aij square is equal to, is easy because Aij's are zeros or ones, let's say for simplicity. So then it is n times D, right? Each row sum, in each row there are n ones, D ones, and D, that will give you D, n times D. Now this is not exactly true. So what is the problem? As I said, lambda 2 tilde is not necessarily the biggest in absolute value. Okay, so what I can write here is not lambda 2 tilde, but what I can write is, let's call it lambda star. It's the maximum of lambda 2 tilde and minus lambda n tilde. So all the other eigenvalues are, other than the first one, are bounded by this in absolute value. So you take the maximum of lambda 2 tilde and minus lambda n tilde. That will give you the bound for absolute values. So that is true. So this is what we will get. So from these two, what do we get? So you take this, what do you get? You get d square minus, this is it nd? Yeah. Something is, so this is d squared, right? So what do I get? Nd, yeah. So I get lambda star squared is greater than equal to d into n minus d divided by n minus 1. Okay, so in other words, so it is like, it is approximately like, so you can say lambda star is greater than equal to square root of d times whatever this quantity is close to 1 if n is large. You can write it as square root of 1 minus n minus 1 minus of d minus 1. And so let's write this. So this looks like a bound like this. There are two weaknesses. One is there is no factor of 2. It's almost is like that. So the factor of 2 missing. Well, you won't get with d, it should be d minus 1. But if you think d also is large, then what is missing on the right side is a factor of 2. But what is wrong on the left side is that instead of lambda 2 tilde. Okay, so I'm calling this lambda star tilde. So this is not lambda star tilde, but lambda 2. I mean, so we get the maximum of the second and this. But this is also good, by the way. So in fact, if you have seen some Markov chain theory, you will know that this is actually what is important. Why is this important? So this lambda star is very important actually. So because in some sense, A is the spectral decomposition of A is A. So if to just explain the Markov chain connection, if you consider random walk on the graph, 1 over dA is the transition matrix for the random walk. For simple random walk on G, meaning you start, the state space is the set of vertices, and from each vertex you move to one of the neighbors with equal probability. That's what the transition matrix tells you. So, but by the spectral decomposition, if I have D here, so all the eigenvalues get divided by D. So I get 1 transpose. That is the first eigenvalue. But then I have I equals 1 up to n minus 1, lambda I tilde over D. Everything has been divided by D. Some Vi transpose, let's say. So Vi are the eigenvectors. Okay. One of the basic theorems in Markov chains is that when you take a to the power, so this one, if we call this p to the power t is going to infinity, goes to the uniform distribution. It goes to, okay, here also actually, sorry, this is not normalized, so I should write here 1 over d. Because 1 over n, 1 over n. Because the constant vector 1 is not normalized in L2. So constant vector divided by root n is normalized. So I should, so in the spectral decomposition, I will have orthonormal eigenvectors. So here I will have 1 over n. So these are orthonormal. So what happens is when t goes to infinity, p to the power t converges to 1 over n indicator 1 1 transpose, which is uniform distribution. It is the all one matrix divided by n. So it's the, so in other words, if you on such graphs, if you start random walk and after a large time, it will be in uniform distribution. It can be anywhere. The uniform distribution is what happens. So p to the t is the distribution of the Markov chain after t steps. So this is telling that after a long time, the Markov chain looks like it is in uniform distribution. But the rate of convergence, why does this happen? One proof is simply here. All these numbers, if they are less than 1, okay, so this needs conditions. So the rate of convergence is really lambda star, because the thing is, each of these terms, n is fixed and t is going to infinity. When n is fixed, the largest of these, all these numbers we are assuming is less than 1. So the rate of convergence is really lambda tilde star over d to the power t. So it goes exponentially, but this is the number. Okay, this is the number. This means that so this is why the lambda star is actually an important quantity that measures the rate of convergence of your Markov chain to equilibrium. And what is the meaning of expander? Instead of just saying lambda 2 tilde is bounded away from D, one way of saying expander is second eigenvalue is bounded away from first, right? But suppose lambda star tilde itself is bounded away from D. So if this is uniformly bounded, so suppose if lambda tilde star over D is less than 1 minus delta uniformly over all n, then you get a uniform rate of convergence of the Markov chains to equilibrium, of the random walks to equilibrium. So these are in. So there's also which I did not touch on, so I'm mentioning it here. So there is a probabilistic meaning to expanders that these are graphs in which random walk converges very fast to its equilibrium. In probabilistic technical terms, it is called very fast mixing. So you have uniformly fast mixing even as graph size becomes large because the expansion is bounded away from this thing is bounded away from 1. Okay, so this lambda star tilde is actually an important quantity. It's not some. Nevertheless, this is a weaker bound to D. Any questions here so far? Okay, so how do you improve it to 2 good D minus 1? So you consider higher powers. The 2k. Okay, so if you consider higher powers, you can get. I will not so trace of higher powers. I will not do it now. You can get to lambda star d greater than equal to 2 square root d minus 1.
So just one thing. So in that lambda star, you are taking max of lambda 2 tilde and minus lambda n tilde. Just the last one, is it? Why
Yeah,
not
so it is. Yeah, I mean, because all the rest are anyway in between. So basically my eigenvalues are,
yeah,
there is
right,
d,
right.
then there is lambda 2, 0 is somewhere here.
And then minus d.
This is, yeah, minus d is here. That may not be an eigenvalue, but lambda n tilde is here. So all the eigenvalues except the last one, except the first one, are bounded by this lambda star tilde. This is the
okay. Yeah, I got it. Thanks. Yeah.
kind of a spectral norm type thing. I mean, for after removing the first eigenvector.
Okay, thanks.
Yeah, it's really P minus 1 1 transpose over n. It's kind of the spectral norm for that. So that is what it is. So by considering higher powers, we can get to 2 root d minus 1. It's actually an interesting proof. I don't know whether I should spend any time on it. Maybe I'll just tell because it's an interesting way of doing things. So how you do it is, yeah, maybe not. It's there. Okay, by the way, I didn't give references. So maybe I'll just give references instead of talking about this. So, but the 2 d minus 1 comes in a nice way. So the reason where this comes from, so the way it comes from is the following. If you consider a d-regular tree, okay, so the number of walks from, let's say, 0 to 0 in 2k steps. How many walks are there in the tree from in 2k steps? I want to start from here, walk on the tree and come back. So that is basically, it is like the Catalan number times d minus 1 to the power k or something like that. Okay, where Catalan number is this 2k choose k over k plus 1. Okay, so this is a nice combinatorial problem. So that the number of walks from 0 to 0 in the tree, in the regular tree, is like this. It is because and trace of 2 to the 2k is really, it is really the number of walks, closed walks of length 2k. on the graph G. Because trace of a to the 2k, if you write it in terms of the entries, you get ai1, i2, ai2, i3, ai3, i4 up to ai2k, i1. So it is how many times you can start anywhere, but you have to come back to the starting point. Okay. So, which is of course, it is approximately like n times the number of walks. But the key comparison is that if you fix the starting point, the number of ways you can return in the graph is more than the number of ways you can return in the tree. That is where you get this comparison. So this comparison is coming from the tree. Okay. So the number of ways you can return in the graph is more than the number of ways you can return in the tree. So if one may use big words, one can say that the tree is what is called a universal cover for the graph. So if you have seen some topology and so on, it's similar to that. So the tree covers the graph. Therefore, the number of ways to return here is more. That's the point. But I won't do this. Let me give some references. So I didn't mention for this whole expander business. So there's a very nice survey. Everyone refers to this. It is by Hui, Lineal, and Wigderson, big names, very famous people. So there is a survey in the bulletin from many years ago. This is a somewhat already, I mean, many things have happened beyond that, but that is still often referred to, and it is a very good, maybe one of the first things that was written as a survey article. They have a lot of applications to coding theory, to probability, many things. We have barely touched upon it. Okay. Then they also then there are many books. So there is a nice book. I like the way it is presented. Kowalski has a book on expanders. I think it is called Expander Graphs. It's available online. So Kowalski is a number theorist. His interest is probably coming from the Ramanujan graph and the number theoretic constructions of Ramanujan graph. It's very nicely written. But there's also many, like if you just type expander graphs, you'll find many computer science lecture notes. So Luca Trevisan has a book, or at least it's an online lecture notes. It's either a book, it's almost like a book, but it could be still in lecture notes form. I do not know if it is published form, but so I will take the proof of the expander graph construction. I will present from here. Okay. But these are all nice references. Okay, now I'll go to the construction of expander graphs. Any questions, comments so far? Okay, so the goal is to construct so these are D regular. So D is fixed such that the vertex size should go to infinity. We want larger and larger graphs, and the expansion coefficient stays bounded below for some h naught. Okay, this is what we want. So equivalent, as we saw, this is equivalent to lambda gn stays bounded below. That we have already seen. Now there are different constructions. One thing, let me just tell it in passing. So side point. So this is a digression. Means not a real digression. Actually, these kind of things were constructed earlier by people like people attribute now some history was lost, and recently people have uncovered. It seems that one of the first people to do something which he didn't call expander but closely to expanders was Kolmogorov. So Kolmogorov in 60s has a paper with some Bardzin, Kolmogorov and Bardzin maybe, I don't know. So they have a paper which is supposed to be basically expanders. But there were people like Pinsker who did it. So there is a random construction which works. Actually, it's a very nice simple construction. Maybe it is due to Pinsker. I'm not too sure of the. I'm not too sure. Okay. So what you do is you take 1 to up to n, 1 dash 2 dash up to n. I mean they are the same. Okay. So it's going to be a bipartite graph. Okay. So it's a GN is a random bipartite graph. So how does this adjacency matrix look? It will have two parts, right? Vn and Vn dash. It has two parts. It has 2n vertices. So there are no edges in the between this part, and there are no edges. So it will be something here and something here. So it will be some B and B transpose here, right? So this is how the adjacency matrix looks. Okay, so what is it? So the definition is B is the sum of 5 random permutation matrices. Okay, so you pick a random permutation out of 1 to n. Okay, so you pick a random permutation. If so, it could be something like 0, 1. So 3 by 3, this is a permutation matrix, right? So you pick 5 random permutation matrices independently, of course, and add them up. In other words, what you are doing is each permutation will tell you how to put one set of edges. If you give me a permutation, I connect 1 to pi 1, 2 to pi 2, 3 to pi 3, and n to pi n. Okay, on the other side. Now you do it 5 times. Okay, so each one on the left side will have 5 edges coming out. So this can lead to multiple edges, but it's okay. Not a C. There won't be too many multiple edges, so we accept that. So it turns out that GN is a sequence of expanders. So you can show that probability that HGN less than equal to H naught goes to 0 for small enough H naught. It's actually, once I have told you this, some of you will be able to do the calculation yourself actually. It's a simple first moment method calculation. You go over all possibilities and see if HGN is going to be smaller than H naught. You have to choose the H naught in the end. But suppose I fix some H naught and look for HGN less than equal to H naught. What does that mean? That means there has to be a set S which has small number of neighbors, right? So you just go enumerate over all subsets of 1 to n and see what's the chance that it has a small set of neighbors, okay? And then you do a union bound and you can get this proof. There is a bit of calculation. It will take an hour at least to do the calculations properly, but it is something more or less that straightforward. But what we do what we will construct is, but this is, we want deterministic constructions. Not randomized. There are many aspects here which I don't appreciate that much. In anyway, I mean, in the sense I don't understand that much. See, in computer science, what is giving a graph? So giving a random graph sometimes may not be good enough. So what is giving a graph on a computer? So you have to, what does it mean? I mean, you will give maybe a matrix or whatever, but there's a complexity issue of checking. So what is it you do with a graph? If you take a vertex, you have to be able to compute who are its neighbors. So there is a complexity issue one has to accompany these questions with. Not only do you want some graphs, in this, the way you construct these graphs, it should be such that you can compute things in polynomial time, okay, in whatever reasonable time. So all those issues are there, but we will not be talking about that. We'll just talk about deterministic constructions. The first one was due to a very famous mathematician, Margulis. In 1980s, he used some rather heavy machinery and constructed it. So Margulis is a very famous person. He's a very famous mathematician. So he used some representation theory and so on. So it was simplified by Gabor and Galil using Fourier analysis. Okay. Essentially, that is the construction we will give. So it's not only simplification, they contributed more. It's not simply some simplification. It was a big simplification, but also it was more quantitative. The H naught in Margulis was not explicit. You get an explicit small H naught for Gabor and Galil. Okay. But the presentation I will take from this thing that I mentioned, look at Ravison's book, where it's nicely presented. There seems to be a little difference. They say it's the Gabor-Galil construction, but from what I see, the Gabor-Galil paper constructs a bipartite graph like this, whereas this Luca Trevisan's and various other presentations of this give not a bipartite one. Okay. Anyway, let's not worry. So what is the graph? Let me describe the graph. Okay, so let me describe Gn. So what is the vertex set? Vertex set is Zn cross Zn, meaning 0, 1 up to n minus 1 cross product with itself. Okay, and what are the edges? I have to describe the edges. So a set, a vertex AB is going to be connected to many things. So I will say what are they? It will be A plus minus 1 B. That means two edges. Everything is modulo n. Okay, all things, all operations here, additions are modulo n. So when I say A plus minus 1, it's modulo n. Okay. So A plus minus 1B, that is 4, that is two edges. Then also A B plus minus 1, that is another two edges. Then here I write S of AB. What is S of AB? S of AB is A plus B comma B. Okay. S of AB is A plus B comma B. But you also connect to, because it is connected to, I mean, the directions are undirected, S inverse of AB, which is actually A minus B comma B. Okay, the way you go from here to here, you subtract the second and so on. Then two more edges. So this is 1, which is 1. So 2 to 4 to 6, 8 edges will be there. T of AB, which is very similar, A comma B plus A. And T of AB, which is the inverse, T inverse of AB, which is A comma B minus A. Is it okay? So these are all the, so by writing this way, you have already made it undirected, meaning if I could have written AB is connected to A plus 1B, AB plus 1, SAB and TAB, and also the reverse way. So what I want is an undirected graph, nothing else is coming in. So this is actually a 8 regular graph. But multiple edges are there. Multi-edges, loops. Because you see, I mean, so for example, if I take 0, 1, it is connected to, if I do A plus, I mean, AB plus 1, it is connected to 0, 2 from here. But also it is connected, if you look at A plus B, what is A plus B? It's also connected to, it's also connected to A plus B will also lead to 0, 2. Whereas A plus B will give to itself. So there are loops and multiple edges, but we don't care. So this is the graph. The claim is that this is an expander sequence. Okay, so we have explicitly described the graph, and this is an expander sequence. It's an expander sequence. Okay. So it's very nicely presented in Luca Trevisan's book. So I'm pretty much taking that. Okay. So any questions about the definition of the graph? It's hard to visualize. Maybe it is good to actually plug it on the computer and see how it looks. I haven't done it. So it's just this description. It's the description is explicit, but it's not clear what it is doing. So in the lineal paper, they say it is mysterious. If it's mysterious to them, definitely it is to me.
It's not, I mean, yeah, one thing is visualizing, but okay, everything has 8, but how do we know that because there are loops and maybe multiple edges, is it obvious it's connected?
It is connected is not too hard because you can keep going in A plus 1B, right? I mean,
I see. Okay. You can just go to one neighbor and then that
Yeah.
way you're, both, all 4 neighbors are covered. Okay, got it. Yeah.
So you can keep going to the right. This picture will be anyway sort of needed for me. So if n is 1, 2, 3, 4, if n is 4, then it will look like this. So n is 5. So here is 0, 0, here is 4, 4. So everything you can always go from 0, 0 to 0, 1 and so on like this. And then you also can go vertically and come back. So everything is connected. It's a connected graph. I mean, part of expander is that it has to be connected. Otherwise, it wouldn't be expander. Lambda 2 would be 0. But connectedness is more direct. Okay, so now how do we do this? Okay, so step 1. So lambda gn, we know, is the infimum over all functions, if you want, from the vertex set to R of the Laplacian f over norm f square, right? Laplacian f over norm f square. So with his, what it means is square. This is the norm squared in L2. What is the Laplacian here? We know that it means, so you know in general, LFF is, you have to take sum over all I adjacent to j, f of I minus f of j square, right? With the appropriate multiplicity and so on. So here that is actually same as, I just write over all u in Vn, f of u yeah, actually maybe it is better for me to write it for directly for the not the Laplacian, but yeah, should I do that or should I do, yeah, so Laplacian should be bounded below, right? Okay, yeah, no, this is okay. Let me try like this. I hope I don't mess it up. F of u minus f of su. Su is one of the edges, right? Squared. But there is also f of u minus f of tu squared, because u is connected also to tu. U is connected to su, u is connected to tu. Also f of u minus f of u plus e1. So this e1 is 1, 0. E2 is 0, 1 coordinate vectors. So that sort of edge is also there. And then there is also the edge connecting to E2. So I don't have to take the other edges because they will come when I am summing over vertices. So when you take the other side vertex, you will get that, right? I mean, so I hope this is clear that if I do this, I get the full. If I miss a factor of 2 and so on, I am not too worried about that. But I think I haven't missed here because I am taking A to these 4 vertices, A plus 1B, A B plus 1, SAB and TAB, and the other 4 are counted when AB is the other end of the edge. So I am summing over all edges. Now, what we will do is that this is true and equality when. So let me remove the infimum and just say that let's say choose F to be the second eigenvector.
No, but this one is, you have to normalize over f, summation f is 0, right?
Sorry. Right. You're right. That when I had written the infimum, I should have done that. It is not over infimum or all f, but over f orthogonal to the first one. You're right. So I'm now it is okay. I'm writing f is the second eigenvector of LGN. Okay, so f is going to be orthogonal to the first one. That is understood. Okay, so this is there. Okay, step 2. Maybe that is okay, too small a step. Step 1 is just writing this. Step 2 is make it continuous. Extend to, let's call it f is a function. Now it becomes a function on 0 cos 0n. Okay, so instead of looking at it as a discrete points, now I look at this as a subset of R2. Okay, so so I go one step more. 0n cos 0n, n is open, so I don't take the next lattice points, so it is open on this side. So this is the point 5 comma 0, and this is the point 5 comma 5 here. So I just take this entire region in the R2, okay, by f of xy equal to just as a piecewise. If
that is n comma 0, right? Not 5 comma 0.
Which one? Yeah, I mean, so here, I mean, see, this was 4, right? 0, 1, 2, 3, 4. I got 5.
Okay, thanks.
Yeah. So it was just for that specific case, I got 5 comma 0. Yeah. Since I had written 4 comma 4 and 0 comma 0 there. Yeah. So if xy is in k plus 1 cos L plus 1. What that means is on each square like this, so if you take this is k comma L, on this square where these two are the dotted things are not included, here it is constant. So f is constant on shaded area. So whatever was the value of the function at this point, of the discrete function small f at this point, you copy that to the whole thing. So it becomes a step function. It's a piecewise, so it's a step function. Okay. So you can form the quadratic form for this. Okay, so consider the quadratic form. Consider, let's call it lambda hat. Okay, so I will drop the code n, which is something like this, but with everything replaced by integral. Okay, so what is something like this? So what I mean is integral over 0n squared and divided by integral over 0n squared of, here I will just take f squared with respect to Lebesgue measure. If you want, f square x dx over this square, and here I will take f of x minus f of sx squared plus f of x minus f of tx squared dx. Okay, it's very similar to this. I just take the first two. I'm not taking the next two for a good reason. Okay, so sx and tx are very clear what they are. Sx is, if x is x1 comma x2, then sx is x1 plus x2 comma x2 mod n, and tx is x1 comma x1 plus x2 again mod n. Okay, so everything is mod n. So this is, we are working in this square now, a real valued function on a actual square in R2. Okay, so this you can consider lambda hat. The claim is lambda is bounded below by lambda hat. Okay, so how does this compare? So define, so this is the definition of lambda hat. I want to compare this to, so how does this compare with lambda? Okay, so first of all, integral f squared is easy. It is just sum over all k comma l, f of k comma l squared, and times 1. The area of that square is 1, right? So you just get that, which is same as L2 norm of, which is same as sum of f of u square. So let's just write it in that form. So it is just sum of, it's actually the same as f of u square. Okay, it is same as f of u square, sum over all the vertices. Okay, so the L2 norm here is the same as that. What about the numerator? Now, what you have to realize is what does this s and t do? Okay, so if you look at a square like this, let's look at a square. So let's look at the simple square 0, 0, and this is 0, 1, 1, 1, 0, 1. What does s do to this? Sx is x plus y comma y, right? X1 plus x2 comma x2. So it will stretch it to this square, rectangle. Is that clear? I mean, the first coordinate will stay between 0 and 1. It's just a linear transformation of this affine, linear transformation of this square to that square, that rectangle. And t will take it to the other way. So t stretches it in the other direction. Okay, so 0, 0. This will be 1, 2. So this is clear, right? So when we look at what is f of sx, so what this means is that f of sx, so the same for any square. If I put kl here, that will go to, if I take this one to be k comma l, if this is k comma l, this will be k comma l, and then s will, sorry, not exactly, what is it?
It should be k plus l, right?
Yeah, right. It is slightly different, but okay. I will, when I write it, all those will get permuted, but the point is sx, the point of this, what I want to say is that f of sx will be, so let's say so let's say x belongs to the square, which is like this, where this is u, and then, okay, so let's say x belongs to that. So then by definition f of x is small f of u, right? Any point here, the value is the point value here at this lower end vertex. So f of sx need not be f of su. It can also be f of su plus e1, because so when you map x, so if this is u, s will map it to su, but if x is here, it can fall here or here. So the integer coordinate for that could be su, or it could be su plus c1. Both are possible. That's why we don't include e1 here. So the numerator, I want to say that it is same as f of u minus f of su squared plus f of u minus f of su plus c1 squared. I think it is pretty much the same thing. Is that sort of okay? I may have lost factors of 2, which I don't want to bother now, but it will be basically that. Okay, so how 1/2, maybe there is a factor of half or something like that. But this is same as this is we can write as now is f of u minus f of su. There is an edge there. See, there is no edge between u and su plus c1. That's why I want to write it as 2 plus f of u minus f of su squared. So a plus b square is bounded by 2a square plus 2b square. So I will write it as f of su minus f of su plus c1 squared. Okay. So this one, because these are edges between u and su, there is an edge. Between su and su plus c1, there is an edge. So overall, as u varies, su will also vary over all vertices. So we'll just get that this is bounded by 3 times sum over all u, f of u minus f of su square plus f of u minus f of u plus c1 squared over all u. Is this okay? Any questions or anything here? So this quantity is basically the same as this. Similarly for t, hence what we see is that this lambda hat that we have written, this is bounded by 3 times the quadratic form for f. It becomes bounded by 3 times lambda. Right? Because the numerator is at most 3 times the numerator here. So from this and this u plus c1 and the s, I got 3 times that. I mean, so bound 3 times that is a bound for this, and this and this 3 times that is a bound for this. So I get lambda hat is bounded by 3 times lambda g. Sorry, something is right. Yeah, this is correct. Is that okay? Okay, so now comes the absolutely key step where you use Fourier analysis. This is where we use Fourier analysis, because now we have functions on a square which we can regard as torus, right? So think of g of x you define as f of, so this is 0 to pi squared, right? So you just define as n over 2 pi x. Okay, so I just regard 0 to pi squared. I mean, there is the natural map from 0n to 0n, that's all. Which is this. So I can do it like that and use Fourier expansion, that's all. So what is so we write g as gx is sum of g hat of, let's call it p over. Now we are doing Fourier analysis in T2. I didn't explicitly state much, but I told you that everything goes through higher dimensions and so on. So we will have here, maybe I write it as p comma q to be explicit. Okay, p is okay, p is okay. G hat of p, EP of, so e to the I times p1 x1 plus p2 x2. Okay, that is how the Fourier expansion of G. Is this okay? This is the Fourier expansion of G. G is a function on the torus. This is how we expand it in Fourier. This one. Now we have to, okay, so there is a small step of relating the norm squared of G to norm square of F, and this one. But what is the key point? Okay, the key point is this, that if you look at, yeah, so okay, so maybe I should do that. So what is the integral over T2 of G square? It will be just 1 by n squared times the
Wait, so Why is that? Well, unless you know something about we have to compute the coefficients, right? G hat before, because the equality are written there.
This one?
Yeah. So to form the Fourier series, but if we know absolutely convergent or something like that, then we can write that it's equal, right? It's
an L2 expansion.
Okay.
Yeah, it's an L2 expansion. That's all I will use. G square x will be like this. Okay. So, but what is the other thing that I need? I need the f of x minus f of sx square. Okay. So what will that be? Again, with a factor of 1 by n squared, this will be integral over g of x minus, maybe I will write it as g of s hat x. Okay, where s hat x is.
It's 1 o'clock.
Oh, okay. I am exceeding time. Sorry. So I'll complete this step and I will leave the rest of it. Okay. So let me complete this step. But s hat is, whatever is s hat x. So s hat x is something such that n times 2 pi that is going to give me sx. So s hat x is 2 pi by n sx. Okay, so that's what it is. Here is the key point. Okay, so if I look at g of sx, what is its Fourier expansion? Okay, g of s hat x. So just look at g of s hat x. G of s hat x is what? It is g of what is it? S hat x is this, means sx is x plus y 2 pi by n into x1 plus x2 comma x2. Okay, that's what it is, right? So which is, let's just write this expansion. As Kaushik said, all this is an L2 expansion. We will see it's all fine. So you write here e to the I times. What do we get? So something is going on. There's 2 pi and so on. I'm getting confused. Why is there 2 pi? Okay, I'm getting confused now. P1, okay, let's do it. Which is okay, so the what we will write is P1 x1 plus P2 into P1 plus P2 x2. Okay, so you get that, which you can write like this. So let's make this as e to the I 2 pi by n. Let's call it q1 x1 plus q2 x2. Okay, so then what is this one? P1 is q1. The second one, P1 plus P2 is Q2, so it is Q2 minus Q1. Okay. So which is, in other words, it is actually, yeah. So what is happening is that, what we are saying is that, so that is, to put it in short, G composed S hat. Okay, S hat was a very bad notation. So let's just call it S. Okay, S tilde maybe. I mean, so it's hat is a bad notation because that's Fourier transform. Okay, so let me just do S bar maybe. S bar. Okay. So what we are saying is G compose S. If you take the Fourier coefficient on the Fourier side, what is it doing? It is taking the Fourier coefficient of G, but applying what is this transformation? It is T inverse, so to speak. Okay. So it would require 10 more minutes to tell properly, but it's kind of clear, right? So Q1, Q2 mapping to Q1, Q2 minus Q1 is exactly this one, right? Except that this T is not modulo 1, not modulo n. This is pretty much like the transformation T inverse, right? So if you remember, T inverse is the mapping which takes AB to B minus A, except that here it is over all Z2. All of Z2, there is no modulo n. So this is not modulo n. Other than that, it is what it is telling. So similarly, what happens is G compose T turns its Fourier coefficient turns out to be G hat compose S inverse, like that. Again, not modulo n on this side. So what is the upshot of all this? The upshot of all this is that this is the point of cleverness. You see, the point of cleverness is why these particular S and T were chosen. The thing is, in Fourier, it's like the difference operator. Okay, so you remember, so when you differentiate it, what it does on the other side, etc., like a shift. So the thing is, G compose S in Fourier case will go to G hat compose T inverse, and G compose T will go to G hat compose S inverse. So that is the cleverness of the choice. Upshot of all this is that this lambda tilde, okay, which we had, lambda tilde is the continuous variational formula, the integral square over integral square. Again, by use of Plancherel, once you have all this, you can use Plancherel. Already on the denominator, I had shown you how to use Plancherel, right? So G square is same as, okay, I hadn't said it. Using Plancherel, integral G square can be written as, so first of all, what I have in the denominator is integral F square, which is up to this constant, which will anyway cancel on the two sides, is integral G square, which is also sum of G hat square. So in the denominator, I will have over P in Z2, G hat of P square. And in the numerator, I will have, because G will go to G hat and G compose S will go to G hat compose T inverse, this whole thing will become exactly the same type of thing with here S and T are ST are defined not modulo n. That's all. So A plus B means A plus B in integers. Okay, so this is the upshot of this. So what we did was from Z mod n, we went to a continuous problem. Now the continuous problem using Fourier analysis, you have transferred to a problem, again a discrete problem, now on Z2. Okay, so let me just say what is the last step. So this looks like second eigenvalue formula for the graph with vertex set which is Z2 except 0, 0 and edges between U and U plus some U plus S U sorry, not U plus S, SU with edges between U and SU, U and S inverse U, U and TU and U and T inverse U. So it is like if you consider a graph with vertices which are Z2 and make up this graph. Okay, then that's exactly this, right? So that's what this is, the sum of squares at the edges. On the edges, you are taking the difference and so on. Okay, so this is looks like the second eigenvalue formula. And what we did, the Cheeger inequality shows that this quantity, this lambda tilde, is greater than or equal to the expansion coefficient for this infinite graph. Cheeger inequality proof. It's not Cheeger inequality because we proved it for finite graphs, but here it is an infinite graph. But Cheeger expansion coefficient for this graph. And the last, so this, okay, this is not the last step. This one, by direct analysis, is greater than or equal to some constant. Okay. So yeah, that last step I am not able to do now. What you have to, now you have reduced your problem to a question of a graph on Z2. Okay. So, and this quantity is like the second eigenvalue formula on Z2. It's an infinite graph. So maybe this needs some technical input to make that precise, but you don't need it to for this. All you need to know is that if you follow Cheeger inequality proof, you can show this is greater than or equal to the expansion coefficient for this graph. Now you have an explicit graph on Z2, okay, where you can analyze directly what is the expansion coefficients, how many things get connected, etc. And I will maybe just refer you to Teresan's notes, and you can show it is bounded below. Okay, I will just stop here. Okay, so that's.
Yeah, thanks, Manju. It was really nice.
Okay, thanks. Thanks everyone for staying. As I said to the.
Wait. So that one you are bound below by that second whatever that G hat, that expression you had.
This
you are
one.
bounding that by the that is like the second eigenvalue, the Rayleigh quotient
formula. And yeah, that's like the second eigenvalue variational formula, looks like that. And you bound it below by the expansion coefficient for that graph, meaning the infimum of the boundary to volume ratio. In an infinite graph, you define the expansion exactly like before.
Yeah, that is okay. No, I'm just checking that. Yeah, we need also the. If it is one candidate, we should check that there is orthogonal to the first.
Right. So the thing is, in infinite graph, it's already, you will have to take some L2 functions and so on. So the constant function is not really, if you are in an infinite graph.
Yeah, that is true.
Yeah, in infinite graph, 0 is not quite an eigenvalue. Okay, in some sense it may be in the spectrum, but you don't have the constant vector.
Right. So okay.
So yeah, but this is over G hat, which are in L2. But the fact that the original thing is orthogonal to 1, that shows up in G hat 0 being 0. That point I did not mention, that G hat of 0 will be 0 because that's the integral of f. Integral of f will be 0 because sum of f is 0. So integral of capital F will also be 0 and integral of capital G will be 0. That goes to the Fourier coefficient. That's why you get this thing over Z2 minus 0, 0. So the original thing being orthogonal translates to this. The origin is removed in this graph.
Okay. Yeah. So thanks very much. Yeah, it was
So Manju, this, I mean, why is this so hard? I mean, given this construction, I mean, if you add instead, I mean, a couple of more, more edges or something like that, like let's say at the next level, like +2 or whatever, then would it not still remain expander?
Yeah, it will remain expander. Why? I mean, you are trying to get to closer to Ramanujan graph or?
No, I'm just trying to think because because I thought you mentioned somewhere that it's this is not easy to construct. So which one is not? I mean, when we are asking this question whether there exists such graphs.
Yeah, so this construction was not trivial. Now the proof is somewhat modular and not difficult in some sense to read, but to come up with this graph was the tricky point.
Okay.
Margulis was not exactly this, but something very close to this. So coming up with this type of graph. So they say this construction is still a bit mysterious. The operation S and T choice is a kind of non-trivial one.
I see. So I see.
Yeah.
So somehow you have short range connection, and then you somehow are exponentially able to grow into the graph or something like
Yeah,
that.
I actually have no picture at all in mind for this. I have no picture in mind. I mean, that only me. I'm just saying. What these people did in this recent Ramanujan graph construction is something that Lineal and others had suggested earlier, which is to keep going from. So if you have a graph G, finite graph, okay, you place two copies of that, one above another, like this. So there are two copies of the same graph. You place one above the other. What you do is for each edge. Okay, so for each edge, there is an edge below and there is an edge above. So let's say this edge, there's an edge below and an edge above. So there are two ways to connect it. So from G to G dash, we are going to a graph with 2n number of vertices. So all these will be vertices. You can keep it like this, or you can connect it the reverse way. You can connect this way. So for each edge, you have to decide which way you want to connect. Either keep them in the original planes, or you connect them across the plane. Okay. So this gives you, if originally there were k edges, there will be 2 to the k different graphs you can get like this. Because for each edge, you have to make a decision. These are called lifts, two lifts of the graph. So the idea was that you pick a random two lift. You start with some reasonable graph. You take a random two lift, then take a random two lift and random two lift and so on. That gives you an Ramanujan graph sequence actually.
I see.
So that is what these people supposedly have done, Nikhil Srivastava and others. So,
very nice.
That at least picture seems okay. They also, I don't see expansion. At least some picture is there. This algebraic one, I have no picture. Yeah.
And in that previous one where you had this bipartite one, this 5, I mean, there's something about this 5.
5 may have been the smallest one needed to make some first movement method work actually there. I think probably, yeah. So I should look it up actually. It's a good point. Why 5? I think, yeah. So it's very clear you can make some large number, but 5 was the smallest one for which the simple first movement method works. I'm not sure if the lower ones are not expanders and stuff like that. I'm not too sure.
Okay. Nice.
Yeah.
Okay. Thanks.
Okay. So then.
Yeah. Thanks, Manju. It was amazing course. Yeah. Thanks.
Thank you. Thanks all.
Yeah. Thank you, sir.